Imagine staring into the cold void of space and catching a glimpse of something that has traveled for 7 billion years just to reach us. A silent wanderer, older than our sun, older than Earth itself, drifting through the cosmic darkness from a star system we may never identify. Now imagine that when scientists finally get close enough to study it, they find something that makes them pause, something that doesn't quite fit the rules we thought we understood. This is the story of 3IATLAS, the largest interstellar object ever detected passing through our solar system. And what astronomers have discovered as it draws near has sparked a debate that stretches from the halls of Harvard to observatories across 6 continents. The data is real, the anomalies are documented, and the questions they raise are the kind that don't come with easy answers. In the summer of 2025, technicians at the European Southern Observatory's Very Large Telescope in Chile began analyzing spectral data from a faint object moving through the outer reaches of our solar system. The instrument they were using, called VES, is designed for high-precision work, capable of detecting the chemical fingerprints of atoms torn free in the vacuum of space. Each spike and dip in the data represents specific elements, a kind of cosmic barcode that tells scientists exactly what an object is made of. And as the team processed the raw spectral lines from 3I/ATLAS, they encountered something they had never seen before in any comet, whether born in our solar system or arriving from interstellar space. The data showed the unmistakable presence of atomic neutral nickel, its signature standing out against the background noise like a beacon in the dark. Line after line matched the known wavelengths for nickel vapor. The readings were consistent, repeatable, and clear. But there was something missing, something that should have been there but wasn't. Iron. For decades, every comet studied in detail has shown iron and nickel together. These two elements are forged side by side in the hearts of dying stars, locked together in the minerals that form when stellar material cools and condenses. They rise and fall in tandem, inseparable partners in the chemistry of the cosmos. But here, at a distance of 3.88 astronomical units from the Sun, only nickel made its mark. The iron that should have accompanied it was nowhere to be found. The team ran every check in the book: bias correction, flat fielding, precise wavelength calibration. They cross-referenced the spectral lines against standard atomic databases, including those maintained by the National Institute of Standards and Technology. The features matched nickel, not molecular bands, not instrument artifacts. The signal-to-noise ratios were well above the threshold for reliable detection. And still, iron remained absent, even in regions where the same instruments had previously detected both elements in other interstellar visitors, like 2I/Borisov. The conclusion was unavoidable. The coma of 3I/ATLAS contained detectable nickel vapor and no iron. The data left little room for ambiguity, but what the data could not explain was how this was possible. How could nature separate two elements that were born together in the furnaces of ancient stars? The European Southern Observatory team described the finding as extremely puzzling. In formal scientific literature, that kind of language is reserved for moments when the data truly defy expectations. Peer reviewers pressed for alternative explanations. Could there be an instrumental artifact they had missed? A misidentified spectral line? Contamination from an unknown source? The team addressed each concern methodically, running additional cross-checks and comparisons. The nickel lines held up. The iron remained invisible. And then came a comment that unsettled even seasoned planetary scientists. Avi Loeb, the former chair of Harvard's astronomy department, read the preprint and flagged something that few had considered. On Earth, he noted, pure nickel without iron is only known to exist in industrial alloys. In nature, these metals are inseparable, bound together in the same mineral structures since the moment they condensed from stellar debris. Loeb was careful not to claim proof of anything beyond natural chemistry, but he forced a question into the open that the scientific community could not ignore. What process, anywhere in the known universe, could create such a signature? The paper offered no clear answer. The puzzle was now visible to the world, and the debate had only just begun. To understand why this discovery matters, you have to understand how comets work. These icy visitors from the outer reaches of star systems are essentially frozen time capsules, preserving the conditions of their formation for billions of years. When they approach a star, the heat causes volatile compounds to sublimate, transforming directly from solid to gas and releasing the materials trapped within. By analyzing the gases that stream off a comet, scientists can peer back in time, studying the chemistry of the environments where these objects were born. The proposed explanation for the nickel anomaly centered on a compound called nickel carbonyl. In industrial settings here on Earth, passing carbon monoxide over finely divided nickel at moderate temperatures creates this highly volatile substance, with the chemical formula NiCO4. It is so unstable that it can vaporize at temperatures where water ice remains frozen solid. When exposed to sunlight or ultraviolet radiation, nickel carbonyl breaks apart, releasing atomic nickel into the surrounding space. The European Southern Observatory team suggested that the comet's nickel could have originated from fragile nickel-carbon monoxide complexes trapped within the icy matrix of the comet's nucleus. At distances beyond 2.64 astronomical units from the Sun, the surface temperature is high enough for nickel carbonyl to sublimate, but not high enough for iron or its compounds to do the same. That threshold would explain why nickel appeared first, while iron remained locked in more stubborn minerals, waiting for the additional heat of a closer solar approach. Laboratory experiments support the volatility of nickel carbonyl. Under Earth conditions, it boils at just 43 degrees Celsius, and under the low pressure of space, it becomes even easier to liberate. No comparable iron compound behaves this way. The comet's chemistry, then, could theoretically result from natural processes in a carbon monoxide-rich, extremely cold environment, where nickel became locked into a volatile carrier while iron remained trapped. This model fits the observed sequence: nickel alone at first, then iron only as the sun's heat increases. It is a plausible explanation rooted in known chemistry. But even with this hypothesis on the table, the anomaly remains. No comet studied before in our solar system or beyond has ever shown this pattern. The mechanism may be natural, but the puzzle is far from settled. What makes 3IATLAS even more remarkable is how close we came to missing it entirely. Long before the official announcement, this interstellar wanderer slipped through the field of view of survey telescopes that never realized what they were seeing. The Zwicky Transit Facility, scanning the skies from Palomar Observatory, recorded a faint moving object on multiple nights in June 2025, from the 14th through the 21st, and then again at the end of the month. But these early detections sat unnoticed in the archives, hidden by the sheer volume of data that modern sky surveys generate every single night. It took a dedicated effort to uncover them. Sam Dean, an amateur astronomer working from home with nothing more than an internet connection and a sharp eye for patterns, combed through publicly available data from the ATLAS survey. He tracked the object's faint trail back even further, identifying images from June 5th through the 20th.
Thank you all for coming. The agency confirms that the Mars Perseverance rover has collected its first sample. We anticipate groundbreaking discoveries in the coming weeks.
Journey, weeks before its official discovery on July 1st. These archival traces were not just a curiosity for historians of astronomy. They allowed scientists to reconstruct the object's brightness and activity well before anyone knew it was interstellar. And what they revealed added another layer to the growing mystery. The TESS satellite, designed for exoplanet hunting rather than comet observation, had captured something unexpected. In May 2025, TESS recorded a faint, steady glow from 3I/ATLAS at a distance of 6.4 astronomical units from the Sun. That is well beyond Jupiter, in a region where most comets remain dormant, locked in ice too cold to sublimate. But 3I/ATLAS was already active. Its coma was bright enough to register in the satellite's photometry, and the light curve showed a persistent rise rather than the flat line expected from a frozen rock drifting in the dark. Engineers at the data center flagged the brightness profile as unusual. They checked for instrumental artifacts, cosmic ray hits, and background stars. Each check came back clean. The activity was real. Something was driving out gassing at a distance where it shouldn't have been possible under normal circumstances. For context, water ice doesn't sublimate until about 5 astronomical units from the sun. Standard comets wake up as they cross that threshold, their tails blooming only when sunlight becomes strong enough to break molecular bonds. But 3IATLAS was active at 6.4 astronomical units, suggesting a mix of highly volatile ices, including carbon monoxide, carbon dioxide, and perhaps even more exotic compounds capable of vaporizing at much lower temperatures. It wasn't just the timing that stood out. The consistency of the signal, night after night, pointed to a process running deeper than surface frost. Something fundamental about this object's composition was different from anything we had seen before. The early activation set the stage for every anomaly that followed. If 3I/ATLAS was already shedding material at such an enormous distance from the sun, what else might be hidden in its chemistry? The question was no longer simply about when the activity started. It was about what exactly was inside this ancient interstellar visitor. Within 2 weeks of the official announcement, observatories across the globe turned their instruments toward the interloper. The Minor Planet Center, based in Cambridge, Massachusetts, logged 122 separate observations in July alone, with data pouring in from 31 different sites scattered across every continent. Photometry from Chile, spectroscopy from Hawaii, imaging from South Africa, time series measurements from Australia. The coordination was fast and deliberate, with alerts moving through professional networks and amateur forums alike, prompting rapid scheduling on everything from backyard telescopes to flagship instruments costing hundreds of millions of dollars. Each new data point refined the calculated orbit, shrinking uncertainties and clarifying the object's path through the solar system. But this initial swarm of observations wasn't just about tracking a moving dot. It was about capturing every possible detail before the object slipped out of reach: its brightness, its color, its coma structure, and the subtle changes in its activity as it fell deeper into the inner solar system. The sheer volume of observations reflected more than curiosity. It represented an entire community mobilizing at speed, acutely aware that an interstellar visitor of this size might not appear again for centuries. Every measurement added weight to the growing data set, and as the numbers stacked up, so did the anomalies. The more closely astronomers looked, the more outliers began to surface, each one demanding explanation, each one pushing the boundaries of what we thought we knew about objects from beyond our solar system. The stage was set for a scientific debate unlike any in recent memory, and the evidence, accumulating in observatories around the world, would soon split the community down the middle. Dennis Bodowitz at Auburn University set out to answer a straightforward question: how much material was this object losing as it swept toward the sun? The numbers he reported were anything but ordinary. At 2.9 astronomical units, 3I/ATLAS was shedding water at a rate of 40 kilograms per second, roughly the output of a fire hose running at full blast, but in the vacuum of space at a distance where most comets remain frozen solid. The mass estimates were even more staggering. Calculations suggested that 3I/ATLAS was approximately 1,000 times more massive than Oumuamua, the first interstellar object detected in 2017. That's not a subtle difference. It's the gap between a city bus and an ocean freighter. Standard models predict that bodies this large should enter our solar system less than once in 10,000 years. Yet here it was, bright, active, and venting material at a rate that stunned even the most experienced comet researchers. When the James Webb Space Telescope turned its infrared eyes toward the visitor, the results added another layer of complexity. The spectra revealed carbon dioxide outpacing water by a ratio of 8-to-1, a proportion almost unheard of in cometary chemistry. Most comets in our solar system barely reach parity between these two compounds. The Webb team published 3 possible scenarios to explain the anomaly: formation in a carbon dioxide-rich environment, billions of years of cosmic ray processing, or an as-yet unidentified mechanism. No single explanation fit the data cleanly. The anomaly stood unexplained. Ground-based observations revealed something equally unusual. Through July 2025, the coma steadily grew redder, a shift tracked by independent observatories worldwide. This wasn't the gentle aging typical of most comets. The change was abrupt, measurable, and consistent, possibly indicating surface alteration or a wave of complex organic compounds being released as the object heated. Polarimetry from the Very Large Telescope delivered yet another surprise. The dust grains scattered light in a way rarely seen outside the solar system's distant icy edge, matching properties of trans-Neptunian objects that orbit far beyond Neptune. Each measurement, on its own, could be explained. Together, they formed a pattern that mainstream chemistry struggled to accommodate. The trajectory added its own puzzle. The orbital path cut through the inner solar system at just 5 degrees inclination to the ecliptic, an unusually flat approach that allowed close passes to Venus, Mars, and Jupiter. Most interstellar objects arrive at steep angles, crossing the solar plane like a dart through a spinning disk. Avi-Loeb calculated the odds of such a low inclination path at roughly 1 in 20,000. Critics called this a statistical fallacy, arguing that rare events are inevitable in a universe of billions of stars. But the geometry remained striking, another entry in a growing catalog of outliers. On October 29th, 2025, as 3I/ATLAS swung around the sun at perihelion, something spectacular unfolded. 7 jets erupted from the nucleus, columns of gas and dust blasting into space. The longest stretched 1.86 million miles, nearly 8 times the distance from Earth to the Moon. These weren't gentle tales. They were violent outbursts, visible even in amateur photographs, shifting hour by hour as the nucleus rotated. The mass loss spike defied easy modeling, rivaling the most dramatic cometary outbursts ever recorded. Amateur astronomers captured the spectacle first, their time-stamped images appearing on forums before professional observatories could respond. For the citizen science community, it was vindication. When institutional telescopes went dark, backyard observers documented an interstellar visitor at its most dramatic. But as the jets faded, a different kind of silence settled in. For 43 days, official channels offered nothing. During the most turbulent stretch of 3I/ATLAS's journey, NASA's public statements stopped entirely. No new data, no press briefings, no confirmation of what amateurs were sharing online. In that vacuum, speculation exploded. University of Washington analysts tracked more than 700,000 social media posts about the object during the blackout, with 40% referencing extraterrestrial origins. Hashtags drifted from astronomy to conspiracy, each new amateur image fueling viral claims about signals, cover-ups, or hidden truths. On November 19th, NASA finally responded. Amit Chatria, the agency's designated spokesperson, delivered the message with unmistakable clarity. This object is a comet. It looks and behaves like a comet, and all evidence points towards it being a comet. The statement referenced ongoing observations from Hubble, Webb, and ground-based telescopes, all finding patterns consistent with natural processes. The message was firm. The extraordinary claims had no support in the data. Brian Cox described 3I/ATLAS as a completely natural object made of carbon dioxide, water ice, and cosmic dust. That assessment echoes the cautious language throughout mainstream scientific literature. When peer-reviewed papers address the anomalies, they do so by stacking natural explanations, not by reaching for the extraordinary. Jason Wright, a leading exoplanet researcher, wrote that the observed outliers are exactly what should be expected from an interstellar comet originating in another solar system, where conditions and chemistry differ from our own. Yet the fine print reveals persistent uncertainty. Roma Maiolo's analysis found that cosmic rays have altered the outer 50 to 65 feet of material, burying any original chemistry beneath billions of years of radiation damage. What telescopes measure now is not a direct record of the object's birthplace, but a surface transformed by eons in deep space. The consensus remains grounded in natural processes, but the papers document how much about this visitor remains unexplained. Avi Loeb formalized his doubts in a peer-reviewed paper, introducing what he called the Loeb scale, a personal metric for weighing the probability of non-natural origin. He started 3I/ATLAS at 4 out of 10. As more anomalies accumulated, he raised the rating to 6. His argument rested on probabilities. Finding an interstellar object this massive should happen less than once in 10,000 years. The trajectory, the chemistry, the early activation, each outlier stacked on the last. Critics dismissed the calculations as post hoc reasoning, but the debate remained alive. How many anomalies are too many before coincidence demands a second look? On December 19th, 2025, 3I/ATLAS made its closest approach to Earth at 270 million kilometers. For astronomers, this was the last best chance to extract answers. ALMA's December observations delivered one final surprise: methanol levels 4 times higher than the typical comets, a key ingredient in the chemistry that builds life's molecular foundations. The object's age, estimated between 7 and 14 billion years, places its formation in the earliest epochs of cosmic history. Its origin remains lost to a journey crossing the paths of at least 25 stars. Its fate is sealed, accelerating toward permanent escape at more than 150,000 miles per hour. 3 interstellar objects have been spotted in less than a decade. Each brings new data and new blind spots. For 3I/ATLAS, the altered surface means any original chemistry is buried beyond the reach of current instruments. No one can identify which star system this visitor called home. The closest look is happening now, and after this window closes, the trail goes cold forever. The final images and spectra will be archived, studied, debated, but the core mysteries, its true composition, its birthplace, the reason for its chemical outliers, may never be fully resolved. Right now, the world's most powerful telescopes are staring at a 7-billion-year-old messenger from the stars. The answers remain just out of reach. Peer-reviewed anomalies and official statements diverge, each side holding pieces of a puzzle that doesn't quite fit together. Science thrives on open questions, on the tension between what we know and what we have yet to discover. Whether 3I/ATLAS is a cosmic fluke shaped by conditions we don't yet understand, or something that will force us to rewrite the textbooks, what we choose to ask next will define what we find. This ancient traveler has crossed the universe to pass through our small corner of space for the briefest moment in cosmic time. It carries secrets locked in ice and radiation-scarred rock, whispers from a stellar nursery that no longer exists, and soon it will be gone, falling back into the infinite dark from which it came, never to return. So I leave you with a question. If you could demand one answer before this visitor disappears forever, what would you ask? What mystery would you solve? Share your thoughts in the comments below. And if this journey through the cosmos has sparked your curiosity, if you want to be here when the next interstellar traveler arrives, subscribe and join us for more explorations of the universe's greatest mysteries. The cosmos is vast, ancient, and full of wonders we are only beginning to understand. And sometimes the most profound discoveries come not from answers, but from the questions we dare to ask.